Welcome. I'm Dr. Ken Piper, and thanks for continuing our miraculous tour through the human body's nervous system. This is part 3 of a presentation called You've Got a Lot of Nerves, and this presentation is part of a bigger series of Wonder Within videos looking at miracles, looking at the wonder of our bodies. The neurologic system I divided into 3 parts. Our focus right now is going to be on the brain, and we're going to look carefully at 4 divisions, 4 different sections of the brain, each section having an increasingly important role in our human day-by-day life and survival. You can see on this MRI that there's a kind of a cord coming up through the neck. That's the spinal cord encased in protective bone from our neck all the way down to our pelvis. Now we're going to start right where that cord comes up into the skull and begin talking about these 4 sections. Now in part 1 we talked about nerves, and just very quickly, every nerve in the body has a cell body that's green. It has little arms and legs with connectors to allow cells to talk to cells, and usually one long arm called an axon that goes down to little terminals. Those terminals may connect with other nerves, or they may connect with muscles and make them fire, or they may connect with little sensor systems to tell us about touch and pain, heat and pressure. Every nerve has some kind of an insulating covering, and those are made of living cells. Those are the red ones that produce this protection. Nerves are also bundled together. So one little nerve is bundled with more, which is bundled with more. So all the nerves in the spinal cord and going down to our arms and legs and eyes and ears, the nerves are protected with various bundles. The spinal cord has huge bundles of nerves. In the orange, you can see the spinal cord running from the brain all the way down to the legs, with some of the nerves that are branching off. And as I mentioned, the spinal cord has got to be protected by the bones of our spinal structure, and the spinal cord is inside that wonderful, encompassing kind of a cage of bony material. So with that kind of background of part 1 and part 2, let's go to part 3 of our series on the brain. And here's the first part of the brain I'd like you to look at. And this is grouping together 3 parts of the brain: the medulla, the pons, and the cerebellum. Now, I'm going to lump those together as if they're one part of the brain. Kind of for clarity, but also for organization, and also because of the integration that's in these areas. And these 3 areas are not involved with consciousness or thinking or any of what we think to be our processing, learning processes. These are all innate systems for survival. So let's show you where they are, and I'm going to talk about the orange. The spinal cord comes up. That first little bulb is the medulla. Above that's the pons, and behind it is the cerebellum. Your eyes are to the left. The back of your head is to the right. The medulla, that little bulb at the bottom, has critical functions. It's the keep us alive center. It has a reflex center for vomiting, cough, sneezing, and swallowing. It has a center for blood pressure control, heart rate, and whether arteries open or close. It controls our fight or flight response, called the sympathetic nervous system, which means when it fires off, it tells the entire body to get ready for trouble, either fight it or run, but you better get ready, and you get ready now. The medulla also is our respiratory center and is controlling our rhythmic breathing. So the medulla is critically important. And all the messages from the spinal cord come up through the medulla, and then they go up into the pons. Now the pons is interesting because it's getting all the messages coming up the spinal cord. It's also looking at all the messages going down the spinal cord. But the pons also gets messages, important messages from the head and face. And those are called the cranial nerves. And cranial nerves, I'll show you a picture of what they look like. This is the bottom of the brain. And all of those yellow things you see are nerves, big nerves coming from various parts of our head and face, traveling through little openings in the bone skull and going down toward the pons. The only nerve that doesn't really go into the pons is the smell nerve called the olfactory, and you can see that at the top of the picture. So the cranial nerves are really important, and don't worry about the details of this, but the cranial nerves are smell nerves in the nose. They are nerves that control the movements of the eyes. A nerve number 7 that controls all the muscles of the face, lips. Number 5 receives all the sensations from the face in 3 different divisions. It also controls jaw muscles. There's a nerve for the tongue, there's a nerve for balance, a nerve for the hearing sensitivity, a nerve to control the muscles in the back of our throat so we can swallow. The vagus nerve, number 10, goes down and talks to the gut brain with messages from the heart and lungs and intestines. So those cranial nerves are pretty important, and as I say, they all travel into the pons. So you can see the pons is getting a tremendous amount of information coming up the spinal cord and from all these cranial nerves that are hooked up with all our main sensing systems. The pons sends a lot of that data back to the cerebellum to be processed. The cerebellum is our movement center. For us to move smoothly, reach up, tie our shoes, bend over, straighten up again, the cerebellum has to take all the information from the pons, make sense out of it, and send down messages so that we can move slowly, control our joints, move our muscles where we want. Without a good cerebellum, we would be staggering, unable to move smoothly, and our life would be greatly affected. Cerebellar strokes are likely to cause some major difficulties for folks. Now, I said the medulla also sends messages for fight or flight. We call that the autonomic nervous system. This we could talk about for an hour by itself. But on the right, you can see the sympathetic nervous system. So when the medulla fires into that system, this is getting ready to flee or fight. Pupils dilate, saliva goes down, heart rate goes up, heart beats stronger, lungs open up, stomach quiets down, liver starts releasing sugar energy, all almost instantaneously. The medulla also can send messages down what we call the parasympathetic system, which really is the calming system. It slows the heart down, it gets the stomach working again. It just sort of calms everything down after a sympathetic stimulation. So I hope you can see that this medulla pons cerebellar team is doing phenomenal things for us, and it's doing it automatically. So when you want to scratch your head, this all happens from those areas. When we climb stairs, we don't think about each step. This system makes it happen. So now let's go on a little bit further, move up in the brain just a bit, and let's go to the second section, which is called the thalamus hypothalamus. And that's just a little above what I showed you. You can see in the light gray there, the medulla working up to the pons. The thalamus hypothalamus is that darker purple area right in the middle. The key thing about this area is now the messages are divided into left and right. Up to the thalamus, everything is coming up in one big channel. But at this point, we start dividing messages to the left side of the brain and the right side of the brain. Now remember, left and right sides of the upper brain do connect, but at the hypothalamus-thalamus level, things begin to shift. The hypothalamus is also a wonderfully unique area where the nervous system, the neurologic system of our body, communicates with the endocrine system. Neuroendocrine, because the hypothalamus is linked to the chemicals released into the pituitary gland. So the brown area on top is the hypothalamus. The nerves up there send messages or chemicals down into the pituitary. And the pituitary controls male and female hormones, bone growth, thyroid control, cortisone production, uterine responses, ovarian responses, thirst, water control. It stimulates lactation for breastfeeding after babies are born. So this thalamus-hypothalamus is the second critical system, and if we go up just a little further, we'll get to the third level, which is called the limbic system. And very simply, the limbic system is our emotional center. At this point, everything's divided into left and right components, and a critical part of the limbic system is called the amygdala. Many of you have heard that word before. Now, it's a little difficult to demonstrate the amygdala, but here's a drawing. In the center of the brain is the thalamus. The blue area is the big connector between left and right side called the corpus callosum. The green area flows out to the side of the brain. You can see a thing called the hippocampus, and on top of that, and the end of it, is the amygdala. The amygdala has a long-term memory separate from other long-term memory centers in the brain. The amygdala remembers the bad stuff. So when I slipped on a big pile of dirt when I was 5 years old and kind of rolled down around a foundation to a house, and there was a little garter snake there. At that moment, I developed a phobia for snakes. My amygdala at that moment imprinted the color of the dirt, the sound as I fell, the thump when I hit the ground, the color of the clouds, and the little snake. And from that point on, if somebody talked about a snake, if someone showed me a snake, or if I thought a snake might be there, any stimuli, my amygdala would fire up and send a response of panic. Stimuli, amygdala, panic for me. And gradually, I'm happy to say I went through a desensitization process with my son and his boa constrictor. And I gradually got rid of that immediate stimulus amygdala response. And all of us have an amygdala full of these kinds of memories. And some stimulus, something we hear or see or even think, can fire off this memory amygdala, and a response occurs that could be anger, it could be frustration, it could be hiding out, it could be running away. But it's a response that is not tied in with the conscious mind. Now, after the amygdala does its reaction, it then sends a message around and up to the conscious brain and says, okay, was this the correct response? I was really worried here. And the conscious mind then has to process it, and often the conscious mind will say, yeah, you're right. You're right. What that person said was exactly right. You did exactly the right thing to scream at them. Now, when I got desensitized enough that when I saw a snake, the amygdala would talk to my upper brain, and my brain would say, okay, so what? You're seeing a snake, no big deal. And the amygdala would not fire off. So a lot of neuroscience right now is looking at, pardon me, the role of stimuli, memory, reactivity, and the way we can develop new circuits to talk between our conscious mind and our amygdala. And this is an area you're going to hear a lot more about in the future. Let's go up to the fourth level of the brain, the cortex. I know you've been interested in this, waiting for it to come. This is our thinking brain. This is the brain at the outer surface of all what's in our skull. And, you know, facetiously, we could say that our brain is about a 3.5 pound structure of thick jello floating in liquid inside this bony skull that we have up on our head. The outer level of that material is called the cortex, and it is not very thick. The cortex is 2 to 5 millimeters thick. The gray matter of all of what we are is in a thin layer covering the outside of the brain. But that gray matter, you can see the gray matter cells on top, send down axons with unbelievable connectivity. 12 billion gray matter cells with tens of thousands of connections in between each cell. It's the most phenomenal integrated system in the universe, and its connectivity is beyond description. Beyond description, the number of ways that messages can be passed around, saved, spread, multiplied. Here's an iPad with, what is it now, 3,200,000 apps, some amazing number. Let's say it's 3 million. Our brain can handle and process every one of those apps at the same time. That's the power of it. And it's doing it as you listen to this little talk. All of your body systems are being monitored, checked, evaluated, adjusted. All your thoughts, every kind of impulse that's going through is happening simultaneously. Our brain has the power to focus and understand and move in directions that are incomprehensible. And we can have a little satellite with a camera fly next to the moon of Pluto and send us back pictures. We divide the outer gray matter into sort of sections. We give them names: occipital, temporal, parietal. What that looks like in a picture is that red in the back is the vision center on the gray matter surface. The blue band is where all the senses go, what you feel and touch, pressure, vibration, hot and cold, all go there. The yellow is called the primary motor strip. So when you think, pick up your hand, that's where it starts. That then goes down, complexity, indescribable, but it goes down and you move your finger. The blue, light blue area in front is the prefrontal and frontal cortex. And that prefrontal cortex is very, very important, because that cortex is where planning, abstract thought, cognition, reasoning, analysis, discovery, those kinds of systems are built in and communicating. This is where consequence and planning get linked up. This is where biases and positions get built up. This is where a lot of circuits develop, some in our favor and some not in our favor. Boys tend to have slower connectivity in that area until their early 20s, which we think accounts for many late teen boys who just don't seem to have an action-consequence connection. And they often don't have a, what I do now can affect me later. How can I plan better now to get the outcome I want? Girls, as they develop, have more of that earlier. So I'd like to give you a couple of examples of what we're talking about. These are just high spots of a few kinds of conditions that involve the brain. And I'm not going to go into detail, but I hope you'll find them interesting. First is stroke. And stroke is a blood vessel blockage that's going to damage the brain cells. This is the new approach we're taking. Many of you understand that when we say heart attack, we want your dad in the emergency room in a cath lab within 45 minutes to go up there and open that blockage and save him from heart damage. In stroke, we're using the term brain attack. We would like to be able to help people with strokes within 60 minutes of the first symptom. So if you see someone whose face looks like it's droopy, or one arm seems to be not working, or their speech is slurred, you call. You call fast and you get 911 help. It's even easier because if someone is just acting odd at the table, go up to them and look at their face. Just say, raise your arms. Tell me your name. And very quickly, you get a sense that this is neurologic or not, and you call for help. Here's someone who was having symptoms. You can see on the right-hand side that there's good blood supply all the way up the brain, but look on the left. The big artery to the left side of the brain is closed. But 20 minutes later, when we were able to open that artery, you can see the entire blood supply has returned to normal, and we prevented a massive stroke. Dementia is basically a memory issue with lots of other parts of the brain that deteriorate. Alzheimer's is the name for about 70% of conditions we call dementia. There's other causes of dementia, and some are preventable maybe and treatable. But Alzheimer's is the most common, 70%. Here is a special scan of a patient with Alzheimer's. On the left is normal, lots of red, that means good active brain. In the middle, there's been some change. On the right, that heavy blue indicates poorly functioning brain tissue, and the red is much less. Here's an MRI scan. On the left is a normal brain. You can see all the white matter, and on that outer layer, the gray matter, the thinking brain, the cortex. Look on the right with Alzheimer's. Look at the shrinkage of the brain. Look at the reduction in those white matter pathways. Look at the increased size of the fluid around the brain and in the middle. This is all the shrinking brain of progressive Alzheimer's. Parkinson's is not a condition of tremor. It's a condition of movement. It's a problem right above the pons where the midbrain is not able to handle the messages and the cerebellum can't do it, and patients start to have a movement problem. The key thing you look for in early Parkinson's with your dad or wife or brother is that when you see them walking, they are not swinging their arms. Reduced arm swinging is one of the early signs. As I say, tremor may or may not be there. The second early sign is they don't take big steps. They start taking small steps, sometimes really small steps, and they have trouble starting their walk. ALS, Lou Gehrig's, amyotrophic lateral sclerosis, ties everything we've talked about together, because this is a dying process that kills a motor nerve either up in the brain, the red, up in the brain, or a motor nerve in the spinal cord, the green. And whether you kill the nerve in the brain or kill it down in the spinal cord, when that nerve dies, the yellow message does not go down to the muscle, and the muscle will atrophy and not work. So ALS is a nerve dying process that shows up with progressive insidious loss of strength. I mentioned before multiple sclerosis. This is an autoimmune condition. The immune system reacts normally to an attack, let's say a viral infection, but then it doesn't turn off, and the immune system begins to fire up abnormally and attack innocent bystander cells like the cells that form the insulation around a nerve. And on the top is a normal nerve cell with its insulating packages. On the bottom is an MS patient with damaged myelin fibers. And when you look at MS under an MRI scan, you can see these little white spots. And the white spots are areas of scarring where damage has been done. And MS lesions can be anywhere, out in the nerves, in the spinal cord, up in the base of the brain, up in the cortex. And most MS patients, and this is a condition that may have a 20 to 30-year course. But most MS patients will have this kind of a scan, one of the ways we look for it. So thank you for your attention. We appreciate an opportunity to talk with you. This is part 3 and a conclusion to a Wonder Within video teaching and learning session on the human nervous system. So I hope to see you again with other series, and thank you.